Hey, my name is Milan, and in this video I'll show you how you can implement full-text search using Postgres. Turns out we don't need any fancy services like Elasticsearch, Lucene, or Solr. Good old Postgres gets the job done just fine. And of course, to make this video more practical for .NET developers, I'm going to show you how we can do full-text search using EF Core. Now, we're going to start with a simple implementation of the default type of search that most people are going to implement. So I'm going to create a get endpoint, and let's call it blogs. And I'm going to be adding the type of search that we're going to be doing in a specific endpoint. So I'm going to say contains, and you will see why I'm doing this. We're going to need a search term, and this is going to be a query parameter. And then I'm going to inject my DB context to perform the actual search. Now, when it comes to filtering my database, the only table or entity that I have is a blog post. And I'm going to say context blog posts where, and then I want to filter my blog post on the 3 columns that I think are relevant for searching. And these are the title, where I can check if the title contains the search term. And we also want to return any records where the excerpt, which is just a short description of what we have inside of a given blog post. And I also want to check the content if it contains a given search term. And we're going to project this result into an anonymous object. So I'm going to return the slug, the title, the excerpt, and let's omit the content because it's a lot of data. Instead, I'm going to return the date. And then I'm going to call toList async. And of course, I will have to await this. So let's introduce a variable. And I'm going to call this blogs, and we're going to await this. Or rather, let's not bother ourselves with async and await and just use good old synchronous calls. And I can return my blogs. I'm running this API using Aspire, and in my setup, I'm creating a Postgres database that I'm adding as a reference to my API project. So this is how my API will be able to connect to a database. What I also have is an initial database migration that is just going to create my table. I'm going to run this at startup. And when it comes to my entity, the blog post is just a plain old C# object. We have just the properties that we need to represent the blog post. I configured the slug as the primary key, but this isn't really relevant for our implementation. Now let's go ahead and start the application. And this is going to open up the resources view on the Aspire dashboard. From here, I can go into the Swagger UI for my API project, and then we can go ahead and search our blogs. And I'm going to search for XUnit because I think this is a nice example to demonstrate how the current search implementation is working. So I'm getting one blog post back, which is about using test containers for integration testing. Now note that the search term I used was XUnit. What if I used uppercase XUnit for some reason? Then in that case, I'm not getting any response back. And if I used XUnit, how it's actually supposed to be written, then I'm getting 2 results back as opposed to 1 result when I'm using the lowercase XUnit. So you can already see that our search is going to give different results based on how we specify the search term. So this is one drawback of implementing the search like this. The second drawback, and this is something that we're going to discuss later, is how we are sorting the results in the response. Typically, when I search for something, I want to see the most relevant result at the top. And in this example, I am getting an article about XUnit as the first result, but this is just by chance. We aren't really sorting the responses when we are returning them from the API. So if we want to improve on the current implementation, I'm going to copy this endpoint, and I'm going to rename this to have normalized in the route. And what I'm going to do here is update the search term by converting it into a lowercase string. And then in my where statement, I'm also going to convert the title, the excerpt, and the content to lowercase strings. So now we are doing so-called case insensitive search. So let's see how this works. So now if I open up the Swagger UI, there is my second search endpoint. And if I type in XUnit, I will get 2 results back. Now, if you recall, in our first implementation, if I used lowercase XUnit, I only get 1 response back. And what's also cool is if I type XUnit, for example, I want it all uppercase, it doesn't matter, it's all going to be converted into lowercase before we perform the search. Now, if I go back to the Aspire dashboard, I can go into my distributed traces, And then let's take a look at this trace here. For the search endpoint doing just plain old contains. Because I have OpenTelemetry, I can take a look at the actual statement that I'm running on my database. So here is my actual query, and I'm going to copy the contents of this query, and then let's open up my resources in another tab, and I want to open up pgadmin. From here, I can open up my database, and what I want to do is open up the query tool, and I want to paste in the query that I just copied. Let's go ahead and align this so that we can see the entire query on the screen. And I will also have to make a change here to replace this with my search term. Now, in order for the like operator to work as expected, we have to specify the wildcards around my search term. So now if I execute my query, I should be able to get a result back, and this is the article talking about test containers. So remember, although we are using lowercase x unit, we aren't doing anything with our columns. If I go back to the Aspire dashboard, and let's go back to the traces. Here is the trace for the normalized search, and this is what it looks like. You will see that we are calling the lower function for each of the columns that we are filtering. So let's update the query here to call the lower function. And I'm going to do this for all of my columns. And then if I execute this request, we get both results back. Now I'm going to make a copy of this query, and let's revert to the previous one. I will add the other query below, and this is because I want to examine the execution plans for these two queries. So I'm going to run explain analyze, and then if we take a look at the analysis, you can see that this query takes about 1.6 milliseconds. Let's run it a few more times for good measure, and you can see that this value stays more or less the same. Now let's check the second query that we have, and this time if I run explain analyze, you can see that the execution time is 5 milliseconds. So this is almost 3 times slower because of using the lowercase function for our columns. So hopefully you can see that this won't really scale well, and it also doesn't give us good search results back. So what can we do about it? Postgres has native support for full text search, and there are two ways to go about this in EF Core. I'm going to show you the more straightforward approach, which requires us to create an index. So I'm going to open up the blog post configuration, and let's say has index. I'm going to write an expression that's going to select the columns that I want to index, and these will be the title, the excerpt, and the content. Then I'm going to tell EF Core to use the gen method for generating this index, and gen is short for generalized inverted index. And this is a type of index that is well suited for full text search. I'm going to leave a link to the documentation below where you can read up more about this, but this is a pretty complicated topic to discuss, but let's just keep it simple. And another thing that I want to call here is define this as a TS vector expression index, and I'm going to specify English for the configuration argument, which is going to determine what is the language that we want to use for our index. Now I need to create a database migration, which is going to look something like this. And the important parts are the annotations here, telling Postgres to use a gen index and also configuring the TS vector configuration to use English. So this is going to be applied to my database when I start the application. And now let's see how we can actually use this inside of our queries. I'm going to copy the original endpoint that I had here, and let's create another implementation. And this time we're going to be doing full text search. In order to achieve this, we have to drop down into the lower level EF Core APIs, and I have to say EF functions and then define my TS vector. And this is how I can tap into the full text search capabilities. Full text search uses the TS vector data type to represent the search data in a way that allows us to easily filter based on the search term and also rank the responses based on relevance. Now I have to use the same value for the config, which is English, and then I have to specify what is my search document. And this is going to be the same values that I use to configure the index. So we have the title, the excerpt, and the content. So this gives me my TS vector. Now I can call the matches method to perform the actual full text search. And I can either pass in the search term directly, which is going to use the plain to TS query function, which is going to convert my search term into a TS query, which can be used for this vector, and it will use the plain2 TS query function. Now there are a bit of nuances to how these functions work. A more robust approach would be using EF functions and then calling to TS query, where I can again specify my language and the actual search term that I want to use. If you're looking for a more robust approach, you can say EF functions, and then you have a couple of methods for creating a TS query. Now there is the web search query, which is going to behave similar to how you do search in the browser. But you can also do phrase to TS query, which is what I'm going to choose here. And then I'm going to specify my config, which is the language, and then the search term value. And this is all I need to be doing full text search. So let's check out how this is working. If I open up the Swagger UI and send a request to the full text search endpoint, and let's use XUnit, you can see that we are again getting the same results back. So nothing too out of the ordinary. If I use a different value like XUnit or even all uppercase, it doesn't matter. The full text search is still going to work as expected, but the interesting part is how this is converted into SQL. So I'm going to take a look at my trace to find the actual SQL query, and you can see the query here. So let's check out the execution plan, and let's just comment on the query as well. So I'm going to show you what's happening here, and I have to update my search term to be XUnit. And if I execute my request, you can see that I'm getting the result back. Now what is happening here is we have a toTS vector call in our where statement, which is going to construct a TS vector from the title, excerpt, and content columns. And then we have a comparison operator here, which is using the phrase to TS query function to convert XUnit, which is our search term, into a TS query. Now if I take a look at the execution plan for this query, you can see that it behaves slightly differently. First of all, we have an index scan, which is going to scan our full text search index that I defined in my EF core migration. This is going to reduce the search space to the 2 records that we have that we are just going to return as the result. Now, if I add the timing here and rerun this, look at the execution time. This is 0.008 milliseconds, whereas we had 1.6 milliseconds when we were using the like operator, and we had 5 milliseconds of execution time when we were normalizing to lowercase. So you can see this is so much faster because we are using full text search. Now in this example, my search space is relatively low, which also has an impact, but regardless, this is going to work so much faster than using the like operator. And now we get to the fun part, which is where we can actually use the full text search capabilities to start doing some interesting things. So I'm going to copy the full text endpoint to create another one, and I'm going to append ranking here. And let me explain why. I can compute the rank of a given result from full text search based on the TS vector. So what I can do here is say EF functions, and then I need to construct the same TS vector that we had earlier. So I'm going to do that. And then we want to call rank. And this is going to calculate the rank for this TS vector based on the specified query. So I'm going to copy the query definition and pass that to the rank method. And the rank value is a floating point result. And then I can use this to sort my results. So I'm going to sort them in descending order based on the rank. So let's go ahead and try this out. So now if I open up the Swagger UI, here is my new endpoint. And now if I type in a query and execute it, we are going to get back this additional rank value that represents how relevant this response is for the search phrase that we use. So you can see that the rank here is 0.09, which is higher than 0.07. Let's try a different query. For example, I want to look for modular monolith, and I'm going to execute this, and I get this response back, the what is a modular monolith article with a rank value of 0.99, followed by the modular monolith data isolation with a rank of 0.95, and then you can see as I keep scrolling down the results list, the rank value keeps becoming smaller and smaller until we get here to an article that is probably about something else, where the rank value is 0.09, whereas the first result had a rank of 0.99, so almost 10 times more. If I go ahead and grab the SQL query for this search, so let me grab it here, and then let's copy to clipboard, and let's paste this into pgadmin, and we'll need to clean up a few things. but most of this will remain the same. So let me just try to fit everything on the screen. And then I'm going to update the search term to be, for example, modular monolith. And I'm doing this just so that we are searching over a large number of records, which is going to make this query slightly slower. So if I go ahead and execute this query, we're going to get the results back. And let's actually place the rank as the first column in the response so that we can actually see the value below. So let me execute this again, and then we get the rank here, and all of our results are ranked based on relevancy. So now this is a huge improvement to how our full text search is working. It's both fast and it also gives the most relevant results at the top. If we take a look at the execution plan for this query, you will see that this query is a bit more expensive. We can utilize the index, which is this part here, to get the response back pretty quickly, but then we have to reach out to the table to fetch the actual rows, and we also have to calculate the rank value, which is the expensive part here, and then the sorting based on the rank isn't all too expensive, but overall I think this is worth it because now we have fully functioning full text search as well as ranking based on a relevance score. And now I want to show you the other way how you can achieve this from EF Core. I'm going to create another blog post entity, and I'm going to call this the blog post vector. And this is because I'm going to add another property here, and the data type of this property will be an npgsql ts vector. And let's call this the search vector. And then we have to configure this with EF Core. So let's extract this into its own file. And I'm going to go into the blog post configuration and use that as the config for my new entity. So this will be a blog post vector. Let's call it the blog post vector configuration, and it can go into its own file. And then we're going to fix the other things. So here we're going to configure this index slightly differently. I'm going to start by saying has generated TS vector column, and we have to add an expression to select this column, which is our search vector column. Then I'm going to specify English for the configuration value, which is the language that we want to use. And then we need to define an expression of the columns that we want to use for this index. So the search vector property, our column, is a computed TS vector column consisting of a title, excerpt, and content. Then I can define an index on this same property. So let's specify the search vector for the index, and I'm going to specify the index method to be gen or generalized inverted index. Let's go ahead and include this in my database context. So I'm going to add another database set, which is going to be blog post vector. Let's call this the blog post vectors. And I'm going to apply the configuration. So blog post vector configuration. Now I need to create my database migration, and this is going to introduce a search vector computed column into our new table with a respective gen index that's going to speed up our full text searches. So this is going to be applied when I start my application. Now I'm also going to update the database seeder to seed this specific table, which is going to include the same data as I had in the blog post, and then I just need to expose an API endpoint that's going to make use of this new column. So let's call this blogs/vector/full-text/ranking because we're going to apply the whole thing. So this time around, I have to use a different database set, and instead of defining my TS vector in the where statement, I can use the search vector, which has a matches function, and I can use that to specify my TS query. I can do the same in the ranking and use the search vector to rank this specific phrase, and this slightly simplifies my query, but let's check out the performance and look at the execution plan. So here is our new API endpoint, and I can specify my search term, let's say xunit. You can see that we get similar results back as previous, and we also have our ranking working as expected. Let's try modular monolith, and if I send this request, we get the most relevant result at the top with the highest ranking. Now I'm going to grab the query that is being used for this particular endpoint, and then let's use it to examine the execution plan. You can see that the performance is significantly faster, but what's also interesting is that we are not using the index. Instead, the query planner is choosing to do a sequential scan on the blog post vectors table, and this is because it can use my search vector computed column to satisfy this entire query. For example, we can directly do a match on the search vector in the where statement, and we can call the tsRank function for this phrase to get the rank value and also sort based on that value. So the reason it's not using the index in this example is because my table is not that large. It only has about 100 blog posts, which are actually the blog posts that I pulled from my website. But if this were a very large table, it would revert to the index because that would give it the result faster. But regardless, I think it's absolutely awesome that you can do full text search with Postgres. And if you agree, then go ahead and smash the like button under this video. When it comes to using this functionality from your code, you will have to accept a dependency on npgsql, either by using EF functions or using the search vector as a computed column, but I think this is a price worth paying if you really need full text search in your applications. And for the end, here is a bonus implementation. I'm going to add another endpoint, which is going to do full text search, ranking the results, and weighing the individual parts of a TS vector. So here's how this works. When you are defining a TS vector, for example, for the title, you can then set the weight for this TS vector using a weight value. There are a few predefined weight values, A, B, C, and D, and A is considered the strongest value, followed by B, and then followed by C and D in the end. And what you can do with these weights is tell the database, or Postgres, how relevant a particular part of a TS vector, in this case the title, is for your search results. So we're going to value matches in the title much more than matches in the content, and then both of these are going to be much more valuable than matches in the excerpt. You can do the same when you're calculating your rank so that these vectors end up being equal. And that's not all. I also have another bonus for you. I also added full text search on my website. So now if you look for something like modular monolith and hit enter, you're going to get the results back sorted by a relevance score. How this worked before was it was sorting them by publication date. So you would get the latest article at the top, even though this wasn't the most relevant article for your search term. But now I updated the search functionality to use full text search. And what's interesting is there is no backend here. The entire full text search works entirely on the client side. And if you're wondering how I implemented this, I'm using a very cool library called Lunr.js, and this allows me to compute a full text search index based on my data and then use the Lunr index to perform full text search. So what I'm doing here, because this is a Next.js website, is computing the index when I'm compiling the website. And this is important because my website is a static application. It's all just HTML and JavaScript and some CSS. And this is the actual part that does the magic. I'm defining a full text search index by calling the Lunr function. Then I'm configuring the identifier of my document. And then I'm defining the fields that I actually want to index. Now I'm also assigning a boost, which is similar to the weight in the Postgres example. And I'm boosting the matches in the title with a factor of 10, and then matches in the content with a factor of 5. And then I'm just adding all of my blog posts as documents to the Lunr index. Now, because this index is pretty large, it's about 2.5 megabytes, and I don't want my client side to be downloading this every time, I'm using Brotli compression to reduce the size of this by about 92%. And then on the client side, when you download that response, I'm going to first decompress it to get the actual index, and then I can use the search index to perform my full text search. And here is what that logic looks like. I have a Lunr index, and I can just call the search method, pass in a query, and map the results back. The result also contains a score that I can use for my relevance rankings. And I'm doing that in the sort function here. So when you get the results back on the website, I'm making sure that you are getting the most relevant result at the top. If you got value out of this video about full text search, then you should subscribe to my channel. And if you're looking to improve your database query performance, then you should watch this video next. Check out my clean architecture and modular monolith courses to improve your skills. And until next time, stay awesome.